Okay, so now let's take a look at an example of an actual related rates problem. And as you can see, this is going to be a so-called word problem, which probably isn't a surprise, right? If you're talking about a real life scenario, how else are you going to communicate it except using words? So that'll be the theme of this section. Now, so if it's a word problem, you got to read it, right? And don't be afraid to read these problems several times, right? That's never a bad thing. In fact, typically when I read these problems, I usually read it once really quick at the beginning just to get an idea of what's happening, and then I go back and read it carefully a second time, at the very least. Okay, so what's happening? Air is being pumped into a spherical balloon. Okay, so you got a balloon and you're pumping air into it. So that the next line is so that its volume increases. And before I go any further, is that a surprise that its volume is increasing? Is that shouldn't really, that's not really new information, right? If you're pumping air into a balloon, the balloon is going to grow and therefore its volume is going to be going up, of course, right? So that's not really a surprise. But the purpose of these words is to say that the volume increases at a rate of 100 centimeters cubed per second. So, okay, forget about the 100 meters, forget about the actual number here, 100 centimeters cubed per second. It's just, the point is, air is being pumped into a spherical balloon and its volume is increasing, and we're told exactly how fast the volume is increasing. That's really all we need to take away from this right now. We can come back to the number later. Now the question at the end is, how fast is the radius of the balloon increasing? So if the volume of the balloon is increasing, then naturally the radius would be as well, right? The radius is just the distance between the center of the sphere and the surface. So if the balloon is growing as you pump air into it, of course the radius is going to also grow. So we want to know, how fast is the radius of the balloon increasing when the radius is 50 centimeters? Well, what's the purpose of that extra bit of information at the end? Why don't they just ask, how fast is the radius of the balloon increasing? And keep it a little bit simpler. And the answer is because then the answer would depend on at which point in time you're inquiring about. If you've ever blown up a balloon before, maybe you were getting ready for a party and you wanted to have some balloons there, think about what happens when it's empty. When you go to blow air into it and you blow it up with just your lungs, your first lungful of air makes a big difference in the size of that balloon, right? And your second lungful of air, maybe not so much. And your third or fourth and fifth lungful, each subsequent lungful of air that you exhale into the balloon seems to make a smaller and smaller difference in terms of how much the balloon grows visually. But of course, every time you breathe, if all your lungfuls have the same amount of air, the volume is going to be increasing with the same amount every single lungful. But with every breath, the radius seems to change less and less, and that's a natural phenomenon. So that's why it actually matters at which point in time you're talking about. So that's the need for that extra information. Okay, so that's the pre-read. We know what's happening. We got air being blown into a balloon or pumped into a balloon. Its volume is increasing at a fixed rate, and we want to know how fast the radius is changing or growing in particular at a particular point in time. So that's the important part for now. All the details we can come back to. So what do you do first for problems like this? Your first step should be to summarize a list of all the variables that you think you're going to need and to clearly lay out what they are, what they mean, and what units they're measured in. That's going to be the first step. So what do you think that we'll need to measure in this question? Well, volume is mentioned early on, right? The balloon's a sphere, it's got a volume, and that volume is increasing at a fixed rate. So let's make up a variable for the volume. How about V, right? That's typically the letter you use for volume. So V is going to be the volume of the balloon, right? And let's take one extra second to specify the units as well. Then we don't have to worry about carrying the units through our calculations. So what units should we agree to measure volume in right off the bat? Well, volume is only mentioned in one place in terms of here, how fast it's changing as the air is being pumped into the balloon. So the volume is changing at a rate of 100 centimeters cubed per second. So it's the centimeters cubed. That's the actual unit of volume that's being used here, right? So why don't we use the same one? That way our volume variable would be compatible with this rate of change here. So let's just put in brackets in centimeters cubed, right? Then we don't have to worry about it as much carrying through our calculations. Okay, What else? What other variable should we introduce? What other quantities mentioned? Well, in the next sentence, it's the radius gets brought up, right? How fast is the radius of the balloon increasing at this particular point in time when the radius is 50 centimeters? So how about r for radius? So we got r for the radius of the balloon. And, well, what should we measure the radius in? Well, this one's a little easier to decide. We're given a particular measurement of the radius at a particular point in time, and it's given in centimeters. So probably we want to measure our radius in centimeters. And that lines up nicely with measuring volumes in centimeters cubed. Then that way everything's going to be compatible. So let's measure the radius in centimeters. Now, are there any other quantities that are mentioned in this problem? Doesn't seem like it, but take a few seconds to convince yourself of that. I mean, you're not going to label the air as a variable or balloon as a variable because those are objects. Those aren't numerical quantities. And by the way, that's actually a common place that people look to cut corners when they're doing this first step. I very often will see things like V equals balloon, or well, how could V is not the balloon, right? V is the volume of the balloon. So be specific. Now, this stage here is not the time to take shortcuts. Take the time to say exactly what you mean and say exactly what the units are measured in. And most of the people that I've spoken with that have struggled with this type of problem at some point, they also skip this part of the problem, or they maybe don't do it completely. So take the time to do this first step completely, and the rest of the process will go much more smoothly. I promise you that. But even stuff like don't go V equals volume, right? That's not specific enough. Go say exactly what it's the volume of. It's the volume of the balloon in the question. So you see what I mean? I'll show you what I mean when we go to the other examples too. You'll see me set an example where I'm really specific, but I'll stop babbling about that now and carry on. So that's the first step, right? Lay out what your variables are and say exactly what they mean. Next, what you want to do is translate the problem into a mathematical one. Just like I mentioned on the previous page, we're going to try to turn these word problems, these related rate problems, into problems that look like these ones, right? We're basically going to try to word it so that it looks a little bit like a problem like this. Now, this is a step that if this is really hard to do, if it doesn't seem like this is going to work, that might mean we're missing a variable. But it'll turn out that it'll work out in this case because we aren't missing a variable. So, well, what are we given? Let's start by identifying what is given to us. Well, we're told right off the bat that the volume of the balloon is increasing at a rate of 100 centimeters cubed per second. So we can express that using a rate of change of the variable v, or in other words, the derivative of the variable v. So really what we're given is dv dt is equal to 100. Right? And here's what I mean. I don't have to specify the centimeters cubed per second because built into the variable v is that it's measured in centimeters cubed. So the centimeters cubed part is obvious, but I do now have to keep track of the fact or remember that time is being measured in seconds for this problem. So at the end of the problem, when it comes time to interpret our results, we'll have to remember that. We have to agree that time is measured in seconds, and then the other two variables here are taken care of already. Okay, so that's what's given. What are we asked for in the question? So what do we want? Well, we're asked in the question, how fast is the radius of the balloon increasing? So really we're asked, what is the value of the rate of change of r? Or in other words, what is the value of the derivative of r with respect to time? So what we want is dr dt, but we want it at the particular moment in time when the radius is 50 centimeters. So really what we should say is we want dr dt when r is equal to 50. That's really what we're being asked. Okay, so this is what it means to translate the problem. Say exactly what you're given and say exactly what we're being asked for. Okay, well, what's next? Well, we need a relationship between the underlying variables, right? If we want dr dt and we're given dv dt, we need a relationship between this rate of change and this rate of change. Well, how are you going to get that unless you have a relationship between the two underlying variables, so r and v. We need a relationship between v and r. And sometimes when you're at the stage and you're trying to find a relationship between the variables, this is where drawing a picture can be really helpful. So, and it doesn't have to be a good one, right? And sometimes you don't even know always the first time what picture to draw. So don't be afraid to draw the wrong picture the first time. Maybe drawing the wrong picture is the first step towards drawing the right picture. So don't be afraid to just jump in and try. But we got a balloon. It's spherical, so I'll do my best to draw a spherical balloon. Balloons have like an air spout, right, where you can pump air into them. So maybe it looks something like that, and it's being placed on. I'm not going to draw the pump that's pumping air into it, right? But that's the idea. If the air would be going in through the hole at the bottom, and well, it's a sphere, so it's got a center, and it's got a radius around the outside, or a circumference, I guess, around the outside. But the point is, if I let that be the radius, hope this is, I didn't draw this too small, it's hard to read. There is a relationship between the volume and the radius. If you're talking about a spherical, I should point to it, if we're talking about a spherical balloon. So what is that relationship? Well, this is this formula. You can look it up, right? It's the formula for the volume of a sphere. It's 4 times pi r cubed over 3. And so that's going to turn out to be exactly what we need. It's a relationship between v and r. And those are the variables whose rates of change we want to find a relationship between. So that's a pretty good place to start. Start with a relationship between the two variables. Okay, then now what are we going to do? Well, now we're going to use this relationship to get a relationship between the rates of change. And how are we going to do that? Exactly how we did it in this problem, right? We had a relationship between x and y, and we needed a relationship between dx dt and dy dt. And how did we do it? We took the derivative of both sides of the equation with respect to time. And that's what we're going to do here. So we have volume is 4 pi r cubed over 3. Now we're going to differentiate both sides with respect to time. So the derivative with respect to time of v equals the derivative with respect to time of 4 pi r cubed over 3. All right, so, well, what can we do? Well, with the v, derivative with respect to time of v, that's just dv dt. Just change the notation, just write it as dv dt. So that dv dt is going to show up in this equation, which is good because then we have somewhere to use this knowledge here that we have. So, but then on the right-hand side, what's going to happen? Well, the best thing to do is probably make it as simple as you can. Notice that 4 pi, that's just a constant multiple, or that's constant multiplier on the r cubed. So constant multipliers can be pulled right out of derivatives. Same with the 3, right? Think of that as multiplication by 1/3. Or really, the constant 4 pi divided by 3, that's what's getting multiplied onto the r cubed. So we can pull that out in front. So we'll get 4 pi over 3 times the derivative with respect to time of r cubed. So it makes it a little bit simpler, right? But now we're going to differentiate the r cubed term. But since it's not with respect to r, it's with respect to t. So we're going to go 3r squared for our derivative of the outside function, but we have to multiply by the derivative of the inside function after. So what we're going to get is dv dt is equal to 4 pi over 3. Then the derivative of the outside function with the inside function left alone. That's the first part of the chain rule, right? That's going to be 3r squared. But now we have to multiply by the derivative of the inside function. And the inside function is r here. So we're going to multiply by dr dt. So that's good. That gives us a relationship between the rate of change of the volume with respect to time and the rate of change of the radius with respect to time. Right? And that's what we need because we're given information about the rate of change of the volume, but we want to find the rate of change of the radius. But we also have an r value in here. So, well, that makes sense because we're interested in a particular point in time when the radius is equal to 50. So it's not a surprise that r ended up being a variable that contributes to this relationship because it matters at how big the radius already is. That's going to help determine how fast the radius is changing. Well, how big is it already? Right? That's an important thing. So that's why r is showing up. So, but we already have a value for r that we're interested in, so we're ready to go. So it's from now it just comes down to solving, isolate for the quantity you're trying to find, which in our case is dr dt, and then plug everything in and find it. So what can we do? Well, we got these 3's can cancel, right? So what we're actually going to get here, if we solve for dr dt, is we're going to, well, we got 4 pi r squared, that's what's going to be left. So bring that over to the other side through division. You're going to get dr dt is equal to 1 over 4 pi r squared times dv dt. Okay, so good. That's looking pretty good. Now, just plug in everything you have, right? We've got r equals 50, and we've got dv dt is equal to 100 at the point in time that we're interested in. So just plug everything in now, and we'll be good to go. So dr dt is 1 over 4 pi times 50 squared, multiplied by the dv dt, that was 100, right? So multiplied by 100. All right, now you can plug these all into your calculator if you want and just get a decimal approximation, but that's as good as you're going to get probably, because there's a pi involved, and if you want to do this all in your calculator, you're not going to get an exact value. But if you do it by hand and carry the calculations through, you can get an exact value, which is what I would like to see. So that's what I'm going to do here. But I will be honest, if you do choose to use your calculator at this point, that's okay too. But let's see what happens. It actually helps to think of this 50 squared. We've got 2 factors of 50 here, so why don't we write this as 1 over, and I'll break the 4 up, and you'll see why in a moment. I'll write the 4 as 2 times pi times 50 times 50, all multiplied by 100, or really we have 100 on the numerator, right? That 100 is going to get multiplied onto the 1 and give us 100 on the numerator. And that's why I broke the 4 up into 2 times 2, because 2 times 50 is 100, so if I cancel out 2 and one of the 50s, that's going to cancel out with the 100. And what you'll be left with, well, there's still 150 left, and there's that 2 left. So 2 times 50 is 100, so you're really going to have 1 over 100 pi. And, well, what are the units going to be in now? Well, now we can easily fill the units in because we kept careful track of what all our variables are measured in. So our radius, which is what we're talking about, the rate of change down here of the radius with respect to time, the radius was measured in centimeters. So really, if this rate of change, this is going to be measured in centimeters per unit of time, which we agreed that time was going to be measured in seconds. So that's how we can interpret this. The radius is changing, or in particular, it's growing at a rate of 1 over 100 pi centimeters per second. So let's finish that off. The radius is increasing at 1 over 100 pi centimeters per second. And that's a complete answer. All right, so that's a related rates problem. Let's go through the key steps here, because this is important, right? The first step, number 1 here, summarize your variables, right? Label and summarize all the variables in the problem that you might need. And if you have an extra one, just don't use it, no problem. It's a lot easier to scratch one off the list once you realize you don't need it than it is to add one after realizing that you should have included it in the first place. So label all the variables. Let's just put it that way to keep it simple. Label all the variables. Step 2, translate the problem. Right? Translate the problem into a mathematical problem. It's a word problem, but you want to phrase it like this so you can solve it using calculus. So translate the problem. So just so we're clear on what's what. Next, find a relationship. And I'm not going to be specific here. I'm just going to say find a relationship, but really we mean something more than that. Not just any relationship, right? I can't just write down absolutely any formula I want, because the likelihood of a random formula solving the problem is pretty close to 0. But you want a specific one, right? You want to find the relationship between the right variables. And the way to determine which variables that is look at what you're given and look at what you want. You need to get a relationship between those two quantities. So whatever the underlying variables are, in this case v and r, those are the variables you want a relationship between. So I'll just say find a relationship between the variables, but you have to use the right variables. What else did we do after that? Once we had our relationship, take the derivative of both sides of the equation with respect to time. I'll just say take the derivative with respect to time. Okay, and then really from there, it's all systematic by that point. Once you get down to this stage, I'll say right here, between this step and this step, this is where we isolated the desired quantity, or I guess we did at this stage. We solved for dr dt, and then we plugged in all the information we had, and you basically cross your fingers and hope that's enough. And in this case, it turned out it was. So just to be consistent here, isolate the desired quantity and plug in the information that you have. I'll say plug in the given information. Okay, so that is how to solve a related rates problem. It really comes down to those 5 steps. And really, the hardest step is usually step 3, finding the right relationship to work with. Right? It doesn't always end up that the first relationship you try ends up being the one that works. So don't be afraid to try and make mistakes, and not your first attempt at these problems isn't always going to work. Don't be disheartened by that, because every time that happens, you're just crossing one thing off your list that's not going to work. So it's not a bad thing to make a mistake on these problems. You're still moving towards a solution. But I've already said this, so I won't spend too much time, but I do want to say it one more time. Please don't skip step 1. Labeling your variables clearly, including the units. This is the key to starting these problems off with setting yourself up to succeed. So don't skip that step or take shortcuts.